Well, welcome to ATMOS 2750, day 10. Today we're going to focus in on the results of the scientific and political efforts to try and remediate the ozone hole. So last time we left off with the scientists figuring out what was causing the ozone hole. And today we're going to start off with the Montreal Protocol, which was the political potential solution for the ozone hole. And then we'll take a look at whether or not the framework that was put in place by the Montreal Protocol is actually working. So what exactly is the Montreal Protocol? Well, the first thing to note is that it wasn't an all-encompassing solution from day one. It was actually a framework set up on how the problem would be solved over time. And there was the realization that the science was not completely understood at the time. In fact, when the Montreal Protocol was drafted, they didn't even understand the significance of the polar stratospheric clouds. Recall that the ozone hole was discovered in 84, 85. The science to try and understand and identify the catalytic destruction cycle was actually done in 86 and 87. So the fact that there was a framework put in place in 87 is quite remarkable. The Montreal Protocol was eventually ratified by 50 countries by 1992, and it targeted the worst offenders in terms of the species that were creating catalysts in the stratosphere. And the worst offenders were CFC-11 and CFC-12, which were the most abundant chlorofluorocarbons, and then some less abundant chlorofluorocarbons, CFC-113, 14, and 15. And the initial framework was that they were planning on having a phased reduction in the production of the CFCs, with a 20% reduction by 1995 and a 50% reduction by 2000. That's all that was in the original Montreal Protocol. For the most part, that's what it was trying to accomplish. It did have some other things that it put in the framework, which we'll talk about now. So it created an international panel of experts that would periodically review the science and provide that information to the United Nations so that they could then try and figure out if new things needed to be done based upon the science. They also recognized that new technology was going to be needed to phase out the use of chlorofluorocarbons. Remember that CFCs are an integral component of many refrigeration systems and air conditioners. And the industrialized countries are in a better position to be able to replace those equipment with things that don't use CFCs rather than the developing countries. And so it was understood that we needed to help the developing countries transition to new technologies. And then, most importantly, as it turns out, the Montreal Protocol initiated a public education campaign to try and make the people of the world aware of what the risks were associated with the ozone hole and what the causes were so far. There were several unintended consequences of this, and one of those is that as soon as you ban the production of a chemical that is widely used in a lot of technology, there are a lot of companies that want to come up with a replacement. And so there was a significant amount of private sector investment to try and find some alternatives to CFCs that could work in these refrigerators and air conditioning systems. It was interesting that there was a partnership between the environmental groups and the industry, and they were actually working together to try and tackle these technological hurdles and to try and figure out how to transition this technology to the developing world. And then the public education campaign was wildly successful. People, as soon as they realized that the things that they were doing every day were having a very harmful effect on the ozone layer, they quickly stopped using products that had CFCs in them, or at least disposable products that had CFCs. Recall that CFCs were used in aerosol spray cans to pressurize the cans. And as soon as the public got wind that their aerosol spray cans were contributing to the ozone hole, they quit buying cans that had CFCs in them, and as a result, the industries had to quickly adapt. And then, of course, when you ban something or phase out its production, it instantly becomes more valuable. And there was before the Montreal Protocol, there were no programs in place to recycle the CFCs. They were just allowed to vent to the atmosphere. But after the Montreal Protocol was put in place, there was now a market for CFCs, and the price of CFCs was going up, and so they actually became a recyclable commodity. And that further reduced the emissions of CFCs to the atmosphere. So the Montreal Protocol was initiated in 1987, but it was always intended that as the science developed, they would expand the chemicals that they were going to focus in on to try and prevent catalysts from getting into the stratosphere. And that's what happened in 1990. The science had identified additional catalysts that should be targeted for phased reductions. And in addition to the original CFCs, in 1990 they added 10 other chlorofluorocarbons with trying to phase those out by the year 2000. They also identified halons, which are used in fire suppression devices. They also identified carbon tetrachloride and methyl chloroform, and they had different reduction strategies trying to phase these out in use, in industrial use over time. So 2 years after that, in Copenhagen, they decided that they could accelerate the reduction of CFCs to completely phase them out by 1996 because the public had been so supportive and had caused the industry to adapt faster than they had anticipated. They also were able to accelerate the reductions of the halons to completely phase them out by 1994. And then one of the replacements for CFCs were HCFCs, hydrogenated chlorofluorocarbons, and they were better for the environment than CFCs, but they were still not the perfect solution. But they were something that could actually be used in the current technology and the current air conditioners and the current refrigerators. And so it allowed the research to continue while the equipment was still being used, so that they could make something that was better than CFCs or better than HCFCs in the future. But there was the recognition that HCFCs were still a problem, and they were targeted for 100% reduction by 2030. The science also indicated that methyl bromide could be a potential catalyst, and so they were trying to cap the production of methyl bromide at 1995 levels. Then it was back to Montreal 10 years later in 1997, and here they were trying to do two things. They tried to enact an import ban on non-participating countries. So non-participating countries who still wanted CFCs would no longer be able to buy them on the open market from recycling programs because they were basically not participating, and this was the one way that the UN could actually have an influence on them. And not only did they enact an import ban, they enacted an export ban on substances that were controlled by the treaty as well, so that you couldn't circumvent the intent of the Montreal Protocol. And the Beijing Amendments in 1999 added yet another species to the list of potential catalysts that needed to be dealt with, and that was bromochloromethane. And they also decided to improve the reporting and tracking for substances controlled by the treaty. So it's not just enough to ban these production and to monitor the recycling. It's also important to be able to quantify the results of the emissions and to keep track of where all these CFCs and HCFCs and halons were actually at in the world, so that they could monitor them and make sure they weren't being released. And then the Kigali Amendments of 2016 targeted hydrofluorocarbons, the HFCs, which are a replacement for the HCFCs. So they were better for the environment than the HCFCs, but are still not perfect. So they're targeting the reduction of those to 85% reduction by 2036. So what do we know about the CFC concentrations? Well, in the 1980s, they were rapidly rising. And when the public became aware that CFCs were harming the environment, they quit buying products. And as a result, and also people started recycling the CFCs as opposed to letting them vent to the atmosphere. And as a result, the emissions of CFCs to the atmosphere quickly decreased, and the natural removal processes were moving on forward, but the lifetime of CFC-11 is greater than 80 years, and the lifetime of CFC-12 is about 70 years. So it takes time for these species to be removed from the atmosphere. But CFC-11 peaked in the early 1990s and has been decreasing ever since, and CFC-12 peaked in the early 2000s and has been decreasing ever since. So let's take a look at the HCFCs, which were the replacement chemical for CFCs. And as expected, their concentrations in the atmosphere were rising as they were replacing the CFCs. But the follow-up amendments to the Montreal Protocol have targeted HCFCs for reductions. And some of these species have started to roll over and have stopped increasing, and we anticipate that that will continue to be the trend as they're phased out, and they'll follow a similar decreasing trend as the CFCs over time. Other substances that were regulated by the Montreal Protocol. Methylchloroform, which is a solvent, has a relatively short atmospheric lifetime, and as a result, once its production was limited, it quickly started to be removed from the atmosphere, and by 2010, about 90% of the methylchloroform had actually been removed from the atmosphere. Same story is going on with carbon tetrachloride, except that its atmospheric lifetime is longer than methylchloroform, and it's going to take longer for it to be removed from the atmosphere. But in the 20-year period from 1990 to 2010, it decreased by about 20%. So other substances regulated by the Montreal Protocol, we have the HCFCs, which are in red and purple, which are basically starting to roll over a little bit. We had the halons, halon 12, 11, and 1301 have basically rolled over, and the CH3BR bromide is also decreasing as well. So what are all of these efforts? Are they making a difference? Well, here we have the time on the x-axis from 1970 to the year 2090. And on the y-axis, we essentially have a measure of the amount of catalysts that are available in the stratosphere for ozone destruction. And they're doing this in terms of the equivalent effective chlorine in parts per trillion. So you can just kind of think of this as how many catalysts are available for ozone destruction. And let's look at the Antarctic region. That is the top line. And initially, back in 1970, the amount of catalysts in the atmosphere was below 2,000 parts per trillion, but it was quickly rising. And by the late 1970s, we know that the ozone hole was forming, and it continued to get worse until the early 1990s. And that is when the concentration of catalysts in the stratosphere actually peaked. And the concentration of those catalysts have been decreasing year over year since then. And then what we have is we have a model that will show what to be expected in terms of the number of catalysts or the concentration of catalysts moving forward into the future under the scenario that the Montreal Protocol keeps clamping down on potential catalysts, and that we don't generate any new species that can act as catalysts that are unregulated. And so what you're going to see is that about the year 2070, is when we're going to have full recovery of the Antarctic ozone hole, when the amount of catalyst is equivalent to what it was back in the early 1970s. So that is a long time for the atmosphere to heal itself, and that's primarily driven by the exceptionally long lifetime of the chlorofluorocarbons in excess of 70 years. So if we look at the middle latitudes, there were never quite as many catalysts available in the middle latitudes, and the ozone destruction that we see in middle latitudes is much less severe than in Antarctic regions. But still, if we think about the ozone destruction that we've observed in middle latitudes starting around 1980, if we continue into the current scenario, that should be fully recovered somewhere around the year 2030 to 2040. And so it didn't have as far to go as the Antarctic, but it's still going to be. So in my opinion, the Antarctic ozone hole is actually a problem that's solved already. We just have to be vigilant to make sure that we continue tracking and monitoring the species that we know are catalysts for destruction of ozone, and make sure that we don't create new chemicals that can serve as catalysts for ozone destruction. If we do that, then the ozone hole is going to recover, hopefully by the end of my lifetime, and certainly before yours.